All right. So I got 4:05, so I'm going to get started. There's people still filing in, but should be fine. This is, of course, COMP2804, Discrete Structures 2, and I'm the instructor, Gerald Hill. So I can't remember if it was you guys or the other section. I think it was the other section. I showed this website too, discretemath.ca. This was put together by people here at Carleton, and it has, well, 1805. I don't remember what's there, but for 2804, if you click on it, they've actually put in old midterms and old finals, and that you can basically take. Right, so they're multiple choice. I can make a selection. I don't even know if that's correct. But yeah, you can try them out and see how many you get correct, and start developing some strategies for the midterm or the test that's coming up. The other website is Wolfram Alpha. This is handy for, now I said when you do your assignments, I would rather you don't reduce it to an integer, but you can do, you can check your work with this, right? So if there's something, if you develop an expression and you want to check it for small values of n and k or whatever you're using, you can actually compute things here. So I can say, 100, choose 3, and that gives me this number. Was that, sorry, was there a question? All right. Yeah, so this is good for sanity checks. So when you develop an expression, you can double check that it actually does work out for small numbers or large numbers if you prefer, but all right. So we're here on the 19th of January. We're going to be taking binomial coefficients. We started them last class, but I think I'm going to go back to the beginning. I think I went rather fast last class. I'm not sure why. And then at the end, I threw a bunch of stuff at you. So I also didn't like the slides, so I rewrote them. So hopefully it's an improvement, but yeah, so binomial coefficients, and then next class is Pascal's triangle, and that's everything that you will see on the test 1, also the assignment 1. But yeah, any questions before we get started yet? Sorry? Pigeonhole's not on the assignment and it's not on the test. Yeah. It'll be on the next assignment with, so yeah, I do kind of, the next assignment is technically recursion plus pigeonhole. Other questions? Okay. So last class, we were talking about binomial coefficients, and one of the things I wanted to do is relate it to what I think is often a common problem when you start counting, and that's double counting. And that's fantastic. Okay. So the first thing I'm going to do, because I did get a lot of questions about this, is let's go back to the password, and I might be giving away some answers to assignment 1, but that's fine. As I mentioned before, I'm not overly concerned about the assignments. Most of the marks are on the tests. So the assignments are for learning. So I don't mind if I give you a couple questions as long as you learn them. So let's say I want a password of length 5 consisting of lowercase letters and digits, and I need exactly 2 digits. Okay, so this is just a smaller version of basically one of your assignment questions. The first thing we're going to do is look at the wrong way to do it, a common mistake that is made, and then basically the rest of the lesson is on binomial coefficients and sort of is the right way to do it. All right, so we're going to define a procedure to generate this password. So I need 2 digits, so I'm going to choose the first digit. There are 10 choices I can make there. And then I'm going to choose a location for the first digit. So I don't know. I have my password is 5 characters long, so there's 5 choices for that. And then I'm going to choose a second digit. Again, I have 10 choices. And then I'm going to choose a location for the second digit. I have 4 remaining locations. At which point I have basically 3 tasks left, but I'm going to sort of roll them all into one. I'm going to put letters in all the remaining locations, right? So, and this is 26 choices for each, and there's 3 spots left. Okay, so using the product rule, I can multiply all these together. But my claim is that you've overcounted or double counted. And so maybe one of the things you can ask yourself is, why did I choose the locations for the digits? Actually, no, never mind. We'll come back to that later. Okay, so I'm going to follow this procedure that we defined. I'm going to do the task 2 different ways and generate the same string, the same password in this case. So this is my procedure. So the first thing I do, I choose the first digit, I choose 2, and then I choose a location. I choose location 5, so I put 2 here. The second thing I do is I choose my second digit and I choose the location, so I choose 1. And then choose letters for the remaining 3 locations. I just choose C. All right, so that's I did the sequence of tasks in one manner, in one way, and I got this string. But now I can, for my first digit, I can choose 3 and location 1. For my second digit, I can choose 2 and location 5. And then I choose all C's again. Now, technically, these are 2 different ways to do these tasks, but they generate the same password. Right, so if I count these using the product rule as I did before, I'm double counting a lot of strings. Basically, yeah, a lot of strings. All right, so that is the wrong way to do it. And I guess one of the a handy way to remember it is if I pick in place. So that means I choose a number and then I choose where to put it. And if I do that more than once, then I probably double counting, because I can alternate. I can pick, I can pick 2 and then location 3, and then I could pick, yeah, basically I can alternate those 2 things and double count. So if I do pick in place, if I have only 1 digit, I can do pick in place. But for 2 or more, then I start double counting. All right, questions on that? Okay, so that is the wrong way to do it. The right way, well, we're going to talk about basically binomial coefficients, and then we're going to look at this, or a similar problem to this later on. We'll solve it with binomial coefficients. Okay, so things that we know for a set S that has size n, the number of permutations is n factorial. We saw that using the product rule. And then for a set S of size n, the number of subsets of size k, well, I told you that it was this notation, n choose k, and my claim is that it is equal to this number here, which we're going to prove in this class. All right, so yeah, n choose k, which is a binomial coefficient, and later we'll talk about why it's called a binomial coefficient. These subsets are all sets, so the order does not matter in this case. I just choose, if I had chose from a set of the numbers from 1 to 10, and I chose 2, 3, 4, or 4, 3, 2, that's the same set. All right, so we're going to prove this by looking at how to choose all sequences of size k from a set of size n, and relating that to subsets. So as a simple example, if I have a set S equal A, B, C, then if all the subsets of size 2, I can write them out pretty easily. A and B, A and C, and B and C. So all the subsets of size 2, there are 3 of them. Now, if I wanted to count all of the sequences of size 2 taken from the elements of this set S, well, I can list those out as well. I have A, B, the same as before, but now the order matters. So I can reverse the order and I count another one. I have AC the same as before, but now I also have to count CA. And I have BC the same as before, but I also have to count CB. So I have 3 subsets of size 2, but I have 6 sequences of size 2. Right. So in this case, one of the ways we relate subsets to subsequences is that if we know the subsets, we can find all of the permutations of all the subsets, right? So in general, we talked about if I have a set of size n, the number of permutations is n factorial. And that also applies for subsets, right? So if I have a subset of size k, then the number of permutations, the number of sequences is k factorial. Okay, so we're going to relate these together, and then we're going to solve for our binomial coefficient. Yes, so in this example, for each subset of size 2, we had 2 factorial sequences, right? So this would be my, if I wrote that as n choose k, in this case, it is 3 choose 2. I get 3 subsets and of size 2, and then I take all the permutations, and there are 2 factorial permutations for each one. Right. So informally, the number of sequences equals the number of subsets times 2 factorial in this example. In a more general sense, we can say that if we have a set S of size n, and we know the number of subsets of S that have size k, then we can find all of the sequences of S of size k by taking the permutation of each subset, right? So that's basically what we did with the previous example, but in a much smaller scale. So we can formalize this idea using the product rule. So I'm going to have a sequence of tasks. My first task is to choose a subset Sk that has size k from my set S that has size n. And then my second task, there are n choose k ways to do this task, right? By definition. So we still don't know what n choose k is, but we're going to use it. Or, well, we know what it is, but we haven't proven it. And then we're going to choose a permutation of that subset, right? So that's all we did before with the sets of size 2. We chose a subset and then looked at all the permutations. So now we can do that for any size set S and any size subset K. And then there are k factorial ways to find the permutation. Okay, so by the product rule, that means that there are n choose k times k factorial sequences of size k in the set S where S has size n. All right. Any questions so far? Okay, so we know the number of sequences, but we have an unknown value. Well, it's known, but we haven't proven it. So what we want to do is we want to, so let the number of sequences of size k in a set of size n be the letter m. So we have m equals n choose k times k factorial. Well, now we can solve for n choose k and say that, well, if I know the number of sequences of size k, then I simply divide by k factorial to get my binomial coefficient. Right? So it's just a little bit of algebra using things that we know. So now we have an expression for our binomial coefficient, but this m is unknown at this point. Okay, so what we're going to do is we're going to count the number of sequences of size k, but just using a different method. And then we'll plug that value in. Okay, so again, you have calculators that can do combinations and permutations? I'll have to get back to you on that, actually. I'll have to take a look at one of these calculators and see, actually. It's been a long time since I've used a calculator. So use the product rule to write a sequence of k elements from the set S, where the size of S is equal to n. So I'm going to define a different procedure. I'm simply going to write k elements from left to right, right? So I choose a subset, the order matters. I'm just going to arrange them from left to right. But instead of choosing a subset, I'm going to choose them one at a time. So I choose one of n elements for position 1. And then I have n minus 1 elements that I have not chosen yet. I choose one of those for position 2. I have n minus 2 elements that I haven't chosen yet. I choose one of those for position 3, etc. And then task k is finally, I have n minus k plus 1 elements left over, and I choose one of those for position k. All right, so that's pretty straightforward, and we've done similar things quite a bit already. So for an example, if I have S and I have 7 elements in S, and I want to choose a sequence of size 5, well, I just, using my sequence of tasks, I choose 4 just sort of arbitrarily. I put it in the first position. Then I choose 2, I put it in the second position. I choose 3, and I choose 7, and I choose 5. Right, so that's one way to do those sequence of tasks. So yeah, that's just a little example. But yeah, so using the product rule, the number of ways to write a sequence of size k is this value here. So we actually have a value now for what we called m earlier, right? But we just want to simplify it a little bit. This is pretty ugly. We've done this sort of simplification before. This expression is sort of a factorial. So we can, basically what we're doing is we're taking that expression and we're multiplying by 1, but we're, writing 1 in a fancy way here. So what this gives us is n factorial over n minus k factorial. So this is our value m that we were looking for. Okay. All right. Questions so far? All right. So we have 2 expressions for m now. The first, we choose a subset, we choose a permutation. So we have n choose k times k factorial. The second way we chose it is just one at a time. We just pick an element, and we have n factorial over n minus k factorial. So these are both equal to m, which means these are both equal to each other. So now I have an expression. I have only one unknown here in a sense, even though we know what it should be. But everything else is well defined, so I can solve for this one unknown just by multiplying both sides by 1 over k factorial. Right, so the k factorials on the left cancel out, and I have this expression on the right. So that's my binomial. And that's a lot of math, which is important, but just generally speaking, we often relate, if we're moving between something that doesn't have any order and something that does have order, the difference in the number of those things is, in this case, k factorial, right? So if I have a set of size k and it's out of order, but I want to arrange them in some sort of order, then that's a factor of k factorial. Anyway, we'll look at more examples like that in a sec. K factorial is the cost of putting subsets in order or taking permutations and making them identical. I would divide by k factorial. Okay. One more way to look at it. If I listed all of the subsets of size k from a set of size n, and then beside each of those subsets, I listed the k factorial permutations, well then, again, I'm left with this expression, and yeah, and it solves for that. So I don't know, a couple different ways to look at it. Maybe one of these makes more sense to you than another, but yeah. All right, so let's take a look at an example of using binomial coefficients to express the fact that order doesn't matter, and then seeing how that changes when we put things in order, right? So let's say I have B beer bottles and C cider bottles. How many ways can I arrange these on a line, right? So I'm just going to line them up, maybe along the stage here, just in a straight line. To start with, all the beer bottles are identical and all the cider bottles are identical, which means that whatever order I line the beer bottles up in, you cannot tell the difference. And whatever order I line cider bottles up in, you cannot tell the difference. However, if I look at each individual location, whether it's a beer bottle or a cider bottle is the difference. Yes? I'm sorry, yeah. The number of, I just wanted to shorten it. It's the number of sequences of size K from a set of size N. Yeah, it's just, it didn't look right by writing out the number of, I just needed some variable there, that's all. Yeah. It represents a couple things. So of course, the canonical answer is that it represents the number of subsets of size K that I can get from a set of size N, distinct subsets. The way we expressed it is we found the number of sequences of size K from a set of size N, and we divided that by K factorial. So yeah, but the actual definition of N choose K is the number of subsets of size K from a set of size N. Yeah, no problem. All right. Other questions? Okay. All right. So all that matters is, so this problem, we all understand what we're trying to count here, number of distinct arrangements where we don't care if two beer bottles are swapped, that's the same thing. All right, so we have, if we look at, let's say that we had B plus C designated locations for these beer bottles and cider bottles, right? So, and technically we sort of do because we only care about the order. So yeah, in my procedure, well, I can define a procedure, but does anybody have a guess as to how many ways I can arrange these bottles? Okay, so our procedure is quite simple. I'm going to choose B out of these B plus C locations for the beer, right? And there are B plus C choose B ways to do that, right? So I have B plus C possible locations. I'm going to choose B of them, and I'm going to put the beer bottles in those locations, right? And then how many ways do I have to place the cider bottles now? One, yeah. One way, right? So I have C locations left. I put the cider bottles there. The order doesn't matter, so I have one way to do that. So the answer to this is B plus C, choose B, or choose C. They're the same thing. But this is if every bottle was identical, except I knew the difference between a beer bottle and a cider bottle. What happens if every cider bottle is now distinct? The beer bottles are still identical, but now the order of the cider bottles matter. So I have to permute the cider bottles, or I have to count the number of ways to permute them. So I'm going to add a third task to my sequence of tasks. And that third task is to choose a permutation for the cider bottles. Okay. So how many ways is there to do that? Yeah, there's C factorial ways, right? I have C cider bottles. Suddenly the order matters. And there's C factorial possible arrangements, right? It's just permutations of a set of size C. So if I add that as a third task, well, then that's just using the product rule. It's B plus C, choose B times C factorial. Okay, so binomial coefficients are good when order doesn't matter. If order matters, you're probably looking at something a little more like a factorial. All right, let's take it a little further. What if now the beer bottles are all distinct? Each one has a different label. So every beer bottle is distinct, every cider bottle is distinct. One way I can do it, I can add a fourth task, which is I'm going to choose a permutation for the beer bottles now. So now I have this expression. However, since every single bottle is distinct and I have B plus C of them, well, then I'm just counting the permutations of a set of size B plus C, which means this should be equal to B plus C factorial, right? And if we actually expand the binomial coefficient, we get B plus C factorial over B factorial C factorial. These cancel out, and that is exactly what we're left with. All right, so yeah. So the order, the difference between a thing that's ordered and a thing that's not ordered is a factor of whatever number it is factorial. All right, so any questions? Simple, right? When you do your assignments, you'll get used to these ideas. Okay, so let's use binomial coefficients a little bit more. So let's say that we have a deck of cards. We have 52 cards in this deck and we're playing poker or whatever. So we're being dealt a hand of 5 cards. So how many hands of 5 cards are there? Now, we don't care the order that we get them because we're going to rearrange them and put the suits together or whatever. But so how many ways are there? How many hands are there? Yeah. Out of a deck of 52? Yeah. No, that's all right. Yeah. Yeah, 52 choose 5, right? So just by definition, it's 52 choose 5, which is, we could expand it out, although I do not expect this. So there's 2.6 million different hands of 5 cards I can get. Okay, it's good questions. All right. So how many bit strings of length n with exactly k many ones are there? So let's take a look. We have, again, we have our bit strings. Each location, this is actually very similar to a problem we just looked at, but so each location, my n locations can be a 1 or a 0,
with card deck,
and I want exactly
with
k
the number
many
of
ones.
possible ways to shuffle it.
What's that?
If you're shuffling, if people shuffled correctly every time, which is not a good
How many of these
assumption,
bit strings
but if
are
they
there?
did, it's likely
So
that
this is
no
really
one
almost
has ever
exactly
shuffled
the
the
same
same
as the
deck,
beer
like
bottle
in the
cider
same
bottle
order.
problem, right?
Yeah.
Except now I have,
Only it
if I think
probably
of
has
0
happened only because
as
of first
beer
shuffling.
No, that's something that
and
it's like not common knowledge, but like you hear.
It's a stat that like doesn't sound like it could be right,
sorry?
and
But then you
do
throw
the
out the
math.
possibility.
Hey, your mic is on.
You do the math, and it's like
Your mic's on.
Yes, please mute yourself. If you have a question, please ask it in the chat. I really can't, I don't have the volume loud enough. All right. So 0 you can think of as the beer, and 1 you can think of as the cider. And they're indistinguishable, right? So if I have a 0 in one location, it's the same as any other 0. Right, so the number of beer in this case is k, or sorry, yeah, sure. And the number of cider is n minus k. So it's just the number of bit strings of length n with k many ones. I'm just going to choose k of my locations out of my n possible, and I'm going to put ones in those locations. Then I can put 0 in all the other locations. Yep. Oh, yeah, in the context of the problem, probably. Yeah, sorry, I didn't really think about it very much. But yes. If one is cider, yes, then K many ones. Yeah, exactly. Thank you. All right. Other questions? I was just thinking about how many confused faces I saw when I did that. But yes, thank you. All right. So yeah, n choose K, and I can do that because the ones and zeros are indistinguishable. So yeah, the chosen positions get a 1, the other positions get a 0. N choose K bit strings of length n with K ones. All right, let's repeat myself a little bit here, but this is in some sense not surprising because by definition, n choose K is the number of subsets of size K from a set of size n. Right, so, and we've already shown a one-to-one sort of a bijection between counting the number of bit strings and the number of subsets of a set. So it's sort of not surprising that this would be mapped, this problem would be mapped to this problem. Right, I can just think of it, I'm building it the same way. If it's, I read my bits, if it's a 1, that element goes in my subset. If it's a 0, that element does not go in my subset. Okay. Yeah, don't worry about it. It happens. I've heard way worse. I swear to God. Teaching over Zoom, somebody, you get a hot mic sometimes, and somebody, all I hear is, I'm in the middle of talking, and all I hear is, what the hell is he talking about? like, if you have a question, just ask. But yeah, he was embarrassed. I was like, no, it's, I don't know. That's fine. Anyway. All right. Let's look at a different version of this. What if we had a string of length n, and we can use any digit, but there has to be exactly k zeros. All right, so our string now looks something like this. We have a bunch of digits, but k of them are zeros. So I have a 0 here, but precisely k many zeros. Okay. So I'm going to use, again, the product rule and some of the things that we know. So the first thing we want to do is choose the locations for the zeros. Right, so our procedure, we're going to choose k locations for our zeros. There are n choose k ways to do that. And this is perfect because zeros, wherever I put them, the order doesn't matter. Right, so this is a perfect application of using binomial coefficients. And then each of the n minus k locations gets one of 9 digits. Right, so these are all the digits from 0 to 9. I have k zeros, and the rest have to be 1 through 9. Right, so how many ways are there to do this? Right, so all this is a string of length n minus k, and I have 9 choices for each character. Right, so I have 9 choices for this, 9 choices for this, 9 choices for this, 9 choices for this. So it is 9 to the n minus k. Right. So yeah. I choose the locations for the zeros, and then the other digits go in all the rest of the locations, but I still have to choose which digit for those locations. Throwing a lot at you today, eh? Questions on that? Okay. All right, so let's look at this one then. We're going to look at another variation. I don't know if I'm giving anything away on the assignment, but as I said, that's fine. We have a string of length n, and now we can use any digit or lowercase letter, but we need exactly k digits. Okay, so again, we'll define a procedure, a sequence of tasks. The first thing we're going to do is choose k locations for our digits. All right, so we have n choose k. Now, each of those digits can be any of the numbers from 0 through 9. Right, so my next task is for each of these k locations, I'm going to choose one of 10 digits. So I just go through, let's say from left to right, I have 10 choices for this one, 10 choices for this one, and 10 choices for this one, and whatever's in the middle. So overall k of them, so that would be 10 to the power k. All of the remaining locations get one of 26 lowercase letters. So I have 26 to the n minus k, the same as I had before. Well, not with digits, though. Okay, so now my using the product rule and binomial coefficients and the things that we know, I get this as the answer. Okay. Yeah, sorry, I'm just thinking about something. Okay, yeah. Any questions? Okay. So that leads into the next thing. Yeah. To be clear, this is permutations, right? These are not permutations. These are, I'm choosing k locations for the digits, but they're not permuted digits, right? They are, each of them can be, I can have all of the same digit if I want, but I might choose different ones. There's complete freedom in how to choose the digits. Couldn't double counting occur? Nope, because once I choose the locations for the digits, if I choose a different subset of size k, I can never get the same string no matter what I choose for these. Right, so, right, for example, if I have, let's say, a string of length 5, I choose a digit here and a digit here, and these are characters. And then I choose, you know, one of 10 digits for here and one of 10 digits for here. This is not maybe 2 and 3. But I'm going to choose all the different combinations that I can. And then when I choose a new subset, well, maybe my digit goes over here. So there's no possible way to double count because the digits will be in different positions. Yeah, hopefully that makes some sort of sense. Yeah, order matters. So these are not, so the locations are subsets, but the characters are not, right? The characters are simply, I'm writing down characters from an alphabet and I can reuse any of them that I want. So technically the characters and the digits are not sets, right? So we don't really refer to them as being in order or out of order. They are simply, it's an alphabet, technically speaking. So yeah, when we're talking about sets, then we refer to being in order or out of order. When we talk about alphabets or characters or digits or bit strings, then the order only matters if we state that in the problem. But when I'm choosing characters, because I can reuse the characters as many times as I want, they're not sets. All right, throwing a lot at you, but yeah. Once you start doing problems, then hopefully some more will become clear. Yeah. Sorry? How the locations are subsets? Okay, yeah. So I have, in this case, a string of 5 characters, and I want to choose 2 of those locations. I can choose 1 and 2, or 2 and 1, right? So the order that I choose these locations in doesn't matter. It's still the same 2 locations. So that's kind of what makes them subsets, because there is no order. Yeah. Makes sense? Yeah, good. Other questions? Yeah.
If you could choose 2 and 2, is it double count?
In this case, I'm only choosing location. So in these questions, there's a lot we're mixing a bunch of the different concepts that we've learned. So this step only chooses locations, not numbers or whatever the alphabet is. Once I have these locations, I know this location needs a digit. I can choose from my available digits. This location needs a character. I can choose from my available character. So I'm really doing 2 steps. One is choosing the locations, which is subsets. Order doesn't matter whether I choose 1 and 2 or 2 and 1. It's the same pair of locations. But then I start putting my letters or numbers in. Yeah, makes sense. It's really, you can think of it almost as, if I choose 2 of these locations, choose here and here, and these have to have digits, I could just think of it as a string of 2 digits plus a string of 3 characters, because in the first step, I figured out what the order is. Yep.
Just clarifying, is that the number of permutations or the number of subsets?
The n choose k?
Yeah, all of the entire thing.
The entire thing. So there's no permutations in this. Yeah, so this is subsets. And then these are basically, this is the password problem, right? So this is, I have a substring of size k, each one gets a digit. So how many ways I can do that? Well, 10 to the power k. Here I have a substring of length n minus k, each one gets a character. So you can sort of think of it as almost 3 separate problems, but all pasted together. Yeah. Yeah. If I understand you correctly, I think you're saying if I gave indexes, like it's just 2 numbers, and then it's just what the 2 numbers, right? Doesn't matter the order. So in some sense, this is like if I had a deck of 5 cards and I dealt you 2. Then you get the cards, you rearrange them in whatever order, doesn't matter. But I have cards 2 and 3. Whether I got 2 first or 3 first, doesn't matter. Does that make sense? So sort of, I don't know. I'm not sure I answered your question or not, but. All right. All right, let's move. How are we doing here? We're here till 5:30. Okay. All right. So this sort of relates. We're gonna again. I'm going to teach you some complicated stuff, and then usually at the end of the class, I go back and do some simple examples when we have time. But yeah, why do we call it a binomial coefficient? So let's look at this expression here, this polynomial x plus y squared. So when I expand it out, I get x squared plus 2xy plus y squared. When I say coefficient, the coefficient of xy is 2, the coefficient of y squared is 1, the coefficient of x squared is 1. Right, so it's just a constant in front of the variables. X plus y cubed, if I expand that out, I get x cubed plus 3x squared y plus 3xy squared plus y cubed. Again, y cubed and x cubed have 1 as coefficients. 3x squared y and 3xy squared both have 3 as coefficients. Okay, so what about x plus y to the 6th? Okay, so now this might get a little messy. I can expand it out in this manner. And then, well, what do I know? I basically know how my x's and y's are going to combine. I'm going to have one term of x to the 6th, one term of x to the 5th y, one term x to the 4 square y squared, etc. Right? So each of these will be represented. All I need to figure out is the coefficients. Okay, so how do I figure out the coefficients? Well, let's say we want the coefficient of x to the 4 y squared. So this guy here. Well, when we multiply these guys out, well, how many ways can I get x4 y squared? Well, each of these terms basically takes a variable from one of these factors. Right, so x4 y squared, maybe I took these x's, these 4 x's, and these 2 y's. Right, so from each of these factors, I take one variable. So then the coefficient becomes, well, how many different ways can I choose 4 x's and 2 y's? Right, so this is another way to choose 4 x's and 2 y's, but how many ways in total? Well, basically, for each of these factors, I can choose either x or y. So yeah, you can think of it as for each factor, I choose either, it's going to be, I'm going to choose the 4 that I'm going to take x from. So I have 6 available. I'm going to choose 4 of those. From those 4, I take the x. From the other 2, I take the y. Okay, so that means my binomial coefficient in this case, well, I did it the opposite way. I chose 2 for the 6, but they're the same thing. Right, so I chose 2 of these factors to take the y out of, and all the rest I took the x. So the coefficient here is 6 choose 2. Okay. Does that make sense? Any questions? Okay. So now I can basically fill in the rest of them. X to the 6, in this case, I'm choosing all of the number that I take y from. If I have x to the 6, then I took 0 from 0 y's, basically. X to the 5y, I chose one of these to take y from. Here I chose 2 of 6, 3 of 6, 4 of 6, 5 of 6, and 6 of 6. And it's the same thing if I chose the x's instead of y. Again, if you recall, 6 choose 6 and 6 choose 0 are the same because they're complementary. If I choose a subset of size 6, then I leave a subset of size 0. 6 and 5, 6 choose 5 and 6 choose 1 are also complementary. So yeah. A nice, easy way to figure out how to expand some polynomial and find the coefficients. Yep. So we're just, yeah. So in this case, I figure out all the ways to multiply these things together. Let's maybe go back a bit so I don't have these. I figure out all the different ways that I can multiply these together. Each time I multiply them together, it's, I'm basically, what do you call that? Distributing these values. So I choose x times x times x times x. So yeah, it's basically an expansion of this thing. So each of these I choose, right, so if we go back to, let's go back even further. So x plus y squared. So that is x plus y times x plus y. If I multiply that out, I get x times x is x squared. And then x times y is xy. Sorry, this is a little bit messy. And then I'm done with this first x. Now I go to the y. I say y times x is plus xy, right? So this y and this x now. And then finally, y times y is y squared. Now the coefficient comes from, I go through and I count the number I have of each of these polynomials, right? So xy here and xy here, I have two of those, so I add them together. Sorry, I lost wherever you were, but. So this is x squared plus 2xy plus y squared. So that's doing it the hard way. The easy way is to say that, well, if I have xy, then the coefficient is the number of ways that I can choose an x and choose a y. And it just so happens that's 2, right? I can either choose my x from here, or I can choose my x from here. So I'm just counting the same thing. Yeah, sorry, I lost wherever you are. But, yeah. So yeah, I expand them, I add up all of the like terms, and then that's where I get my coefficient. But we can do that using a shortcut by using the binomial coefficients. Questions? Yeah.
Yeah, so I was thinking, so I guess binomial coefficients is another way to do quantitation. Like out of all these x's, choose the x's and also y's as well. And those y's will choose the x's and also the y's as well.
Right. So when I choose, so I think I heard you say permutations. So it's not permutations, but yeah, when I choose, then, you know, I have the terms from left to right, and I choose, when I choose the x's, I also implicitly choose the y's. Yeah. Yeah. But that's, I think that's what you said. Yeah. Okay. Yeah. Does that answer your question? Yeah. Yeah. Okay. Other questions? Okay. All right. So if in general, this is called Newton's binomial theorem. So x plus y to the power n. So this is basically what we were just looking at, all of these polynomials. If I expand it out, in general, I get, you know, n choose 0, x to the n choose 1, x to the n minus 1y. And in general, I sum up from k equals 0 to n choose k, x to the n minus k, y to the k, or actually the order, whether I put k on the y or k on the x doesn't actually matter. They will both be the same. But yeah, so this is called Newton's binomial theorem, and it's a useful way to count a lot of different things. So yeah, let's do an example. Well, this is not an example of counting, but let's find the coefficient given x plus y to the 75. What's the coefficient of x to the 50, y to the 25? So the coefficient is the constant in front of this polynomial. So yeah, what is it? Yeah. Yeah, or 75 choose 25. Those are both the same, right? So that's it. I have 50 x's and 25 y's chosen out of a possible 75. So I can do 75 choose 25 or 75 choose 50. So yeah, that's my coefficient. In this case, it's that simple. Yeah, actually, does everybody get this? Any questions? Okay, so let's make it a little more complicated. Let's say I have 3x plus 2y to the power 10. Now what's the coefficient of x cubed y to the 7? Now it's not quite so simple because we have constants in front of these. So what we're going to do is we're going to put it into a form that we understand. We're going to make x prime equal to 3x and y prime equal to 2y. And we're going to rewrite this expression as x prime plus y prime to the power 10. Now we know this is our coefficient, and this corresponds to, yeah, sorry, maybe got a little ahead of myself. So y prime to the power 7 is going to be the same as y to the power 7, as we'll see in a moment. But yeah. if I use Newton's binomial theorem here, and then I plug in, so y is to the power 7, so this is for k equal to 7. Then I get, yeah, so there's a lot going on here, but I, of course, where are we? So y to the 7, I'm going to choose 7 of the y's, or y prime in this case. Once I substitute back in 3x for x prime and 2y for y prime, I have 3x to the power 3 and 2x to the 7. Right, so now this polynomial is on the whole, is on 2 and y together, not just y. Since this is multiplication, it's commutative, so I can move these around however I like. So I can move, well, actually, first I multiply out this exponent to the 3 and to the x and to the 2 and to the y. And then I move my constants and I gather my variables together. Okay. So now what is my coefficient? Well, I actually have to factor in these constants as well. So my coefficient is now this entire thing. And this is my variable part, right? So the coefficient of x cubed y to the 7, we want the term corresponding to, from Newton's binomial theorem, when k is equal to 7. Then I have to take into account these constants. And yeah, this is my final answer. Any questions on that? Yep. K equals 3 would also be acceptable? X to the, yeah, if you chose x to the 3, you mean? Is that? Well, you have to, it has to be y to the power 7, whatever you choose for k, does it? Yeah, it doesn't matter if I choose n minus k on the x or k on the x or vice versa. That doesn't matter. It's not going to change your numbers. But when I ask for the coefficient of this, make sure that the y value has the 7 exponent. That's all. Other questions? Yeah.
I know that's like I guess not like the decimal answer, but would you want us to leave it like that or get it to an actual number?
I prefer you leave it like that. Again, this is as clear to me or more clear than any number. Yeah. Other questions? Okay. Yeah.
Yeah, so on the assignment, I would get better than but would you provide the K in the assignment? We have to solve it.
I think, did I give you questions like that? I think I did, eh? I asked you for a coefficient of, it's a little, I think I gave it a little twist though, but yeah. I believe I gave you exactly or sort of exactly this question. All right, let's put one more little twist on it. Now we have 7x minus 13y. So this again, so what's the coefficient of x to the 50, y to the 25? This is raised to the 75. All right, so again, I'm going to substitute in x prime for here and y prime for here, but I'm going to, I'm not going to do it explicitly. I'm just going to do it implicitly. So using Newton's binomial theorem, I know that the y has to be raised to the 25. So here my k has to be 25. So then I can write out that term as 75, choose 25, 7x to the 50 minus 13y to the, this should be 25. Okay. This is equal to 7 to the 50 times x to the 50. And now this minus 13, I'm going to break it down into 13 and minus 1. Right? So yeah. Again, if you use k on your y term, the most important thing is to get y raised to the right exponent or x raised to the right exponent. that they are, one implies the other. If y is raised to the 25, x must be raised to the 50 in this case. So yeah, just make sure you get your exponent correct, whether you use n minus k here or k, that doesn't really matter. If you mix up the order, as long as you get the right number substituted in for your k. All right, so here I've broken down minus 13y into minus 1 to the 25, 13 to the 25, y to the 25. So what does this mean now? So this, of course, everything looks good except for what is minus 1 to the power 25? Sorry? Yeah, it's minus 1. What if it was an even number? Yeah, just 1. So when you have a negative, whether the exponent is odd or even is going to affect the final value. So in this case, it's negative because minus 1 raised to the 25. So yeah, my coefficient here is all of this. Yep. Yeah, that's probably fine. As long as it's clear that, because if you left it as negative 13 to the power 12, then that's even. So, don't do that. Don't leave a negative in it if that negative is going to be disappearing. I guess it would be better if you brought it up front. That's more clear. Yeah. All right. Other questions? All right. What did I do here? Did I skip one? Okay, so yeah, Newton's binomial theorem. So let's say we just took the sum of all of these. So k equals 0 to n of n choose k. So expand it out, that is n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n. And if we take Newton's binomial theorem and we say x is equal to 1 and y is equal to 1, so now we're substituting values in for x and y. Well, then x plus y to the power n equals 1 plus 1 to the power n, which is equal to, this is equal to 2 to the power n. And if I use Newton's binomial theorem and I plug, 1 in for x and 1 in for y, then I get n choose k times 1 to the n minus k times 1 to the k. Each of these is, of course, just equal to 1. 1 raised to any power is equal to 1. So this is equal to, this original expression. So all of this is equal to 2 to the power n, right? Yeah, okay. So that's fine. Why is that important? Well, is there another way to argue this? So let's say that, let's count it in another way. So we're going to map it to another problem. We're going to say, we know that if we have a set of size n, the number of subsets is 2 to the power n. Now I'm counting all subsets, not just the ones of size k, but all subsets. And we argued that earlier using the product rule. So now what we want to do is we want to say, well, this also counts all subsets of a set of size n. Okay, and all we're going to do is basically explain that it does. So how many subsets of size 0 are there in a set of size n? Well, there's n choose 0. And then I want all the subsets of size 1. Well, there's n choose 1. All the subsets of size 2, there's n choose 2. And I can go through all of the possible numbers until I find all the subsets of size n, there's n choose n. Right, so I'm arguing here, not really mathematically. I'm just explaining that, well, if I count all of the subsets this way, and I already know how many subsets there are of a set of size n, then I can prove that this is equal to 2 to the power n, right? Just by saying, well, this represents taking all of the subsets from a set of size n. Right, so this is called a combinatorial proof, right? So I'm going to, there's something I have that I already know how to count, and I have another problem, and I'm just going to say, well, you know, this counts it, but in another way. It counts the same thing, but just using another technique. All right, questions? Okay. A couple more things. This is, maybe I made these slides too long, but all right. So we could argue, again, we're going to argue this combinatorially. We've seen this actually, and I've said it multiple times. But n choose k is the same, same as n choose n minus k. Every time I choose a set of size k, there's a complementary set of size n minus k, right? And we can use the formula. Yeah, so n choose n minus k, if we expand it out, it resolves to the same thing. However, we want to just prove it using counting or a combinatorial proof. So basically, the combinatorial proof is the same thing I've been saying all along, is that every time we choose k elements from a set of size n, there's a corresponding set of size n minus k. So whether I choose the k or the n minus k is in some sense the same thing. Right. So that's one combinatorial proof that we've seen many times. Here's another one which relates to Pascal's triangle, which we're going to look at next class. But if I have n plus 1 choose k is equal to n choose k minus 1 plus n choose k. So this is math. It looks ugly and, you know, maybe not exciting, but what I'm going to do is explain what these things are counting and why they both count the same thing. So in the first case, n plus 1 choose k, I have a set of n plus 1 elements, and I'm going to choose k of them. And then I want to argue that this is the same as these two things. All right, so how can I do that? Well, what I'm going to do is, I know this is choosing a set of size k minus 1 from a set of size n. I'm going to make one element a special element. Right, so I just choose one, doesn't matter which one, and I'm going to say this is my special element. And then I'm going to count the number of subsets of size k that include this special element. Right, so how many are there? Well, we can, in some sense, all of these subsets have to include this element, so I have no choice in that one. That goes into the subset. And now I have to choose another k minus 1 elements to complete my set of size k, right? And those k minus 1 elements, I have to choose from a set of size k because the special element, I don't have a choice in this, right? So step 1 is I find all of the subsets of size k that include the special element, that is n choose k minus 1. And then I can find all of the subsets that don't include this special element, right? In that case, if I know they don't include, then I'm choosing from a set of size n, and I have to choose k elements from that set. All right, so as long as k is at most n, then n plus 1 choose k is all of the ways to choose subsets of size k with my special element, plus all of the ways to choose subsets of size k without my special element. Right? So this is a combinatorial proof of this, just using words, basically. Does that make sense? Any questions? Yes. Of course, we have to ask ourselves, are these sets disjoint? And yes. Right, so all of these subsets of size k, all the ones that contain the special element, have to be disjoint from the ones that don't, because there is at least one element difference. Yeah, so that's an example of a combinatorial proof. I think that takes us to the end of this. Any questions on that?
Yeah, can you just minus one, just re-explain the Pascal's triangle again?
This is, so Pascal's triangle, we're going to take that next class. This is one, so I can very quickly go over what Pascal's triangle is. I start with 1 along the outside, and then for an inside, so every row I add one more element. And on the inside, I add the 2 rows or the 2 elements that are above it. So this would be 2, this would be 1. 1 on the outside, here I add 1 and 2 together, I get 3. 2 and 1 together, I get 3, 1. And I keep going, I can go for infinity. So that's Pascal's triangle, and that actually, where I take the 2 and the 1 and I add it to the 3 is actually this expression. So we're going to show that next class, but that's why we called this an example from Pascal's triangle. Yeah. Other questions? Okay. So we have about 10 minutes left. So I'm going to, usually what I do is after all this, I go through an easier example that sort of just sort of review the concepts, but on something that's not quite this intense. So yeah. We'll just go over some of the exercises, some of the simpler ones from the book, and then, just work out problems that are hopefully a little bit lighter. So in this example, I have a set of elements A, B, C, D, E, F. Or E, F, G. There are 7 elements in it. And I want to count permutations, but I want permutations that do not contain B, G, E in that order, and do not contain E, A, F in that order. And I want to prove that that's equal to 4806. Okay, so this is combining a lot of different things, but something that's relatively simple, but just a lot of steps. Okay, so what I want is permutations that do not contain BGE, I'll write it like this, and do not contain EAF. How am I going to count those? It seems really difficult, right? Because I can have a B and I can have a G, and if it's followed by an F, that's okay. So that's going to be really weird to count. So what we do when things are hard to count, we use the complement rule, right? Or we can try the complement rule. So the complement rule, I want to take all permutations and then subtract the complement of this. Okay, so all permutations of a set of size 7, how many of those are there? I hear a lot of whispering. I'm sorry, I didn't hear any. Yeah. Yeah, 7 factorial. Right, so that's simple enough. 7 factorial, and then I'm subtracting this expression. So what I'm going to do here is I'm going to apply, we're using a bit of our set theory here, so I'm going to use De Morgan's law. All right, so what that means is that I have some expression, in this case, B and G, let's say. I take the negation of it, that's equal to not B or not G. So this part of our expression is equal to not BGE or not EAF. These double negatives, they cancel them out, right? The complement of a complement is just the set itself. So I want all permutations minus BG, all of the permutations with BGE or all of the permutations with EAF. Okay, so I just need to count this now. So how many permutations contain BGE? All right, so here's what we do. We know that BG and E have to be together. So when we look at our set of characters, we say, well, we have an A. I can't use B because B is going to be with this set of letters. So I have an A, a C, a D, a B, G, E, an F, and a G. So I'm going to count B, G, E as a single character, right? Because I know they have to be together. So now I want the permutations of a set of size 1, 2, 3, 4, 5. Did I put too many? 6. Oh, the G, right. All right. So 5, yes. So all of the permutations that contain BGE in that order is what? 5. There's 5 elements, but how many permutations of this? Right? 5 factorial, exactly. So BGE is 5 factorial. So this is minus 5 factorial. Let me just get myself some space. 7 factorial minus 5 factorial. This or, so that means I use either inclusion, exclusion, or the sum rule, right? It's the union of 2 sets. But regardless, all of the sets or all of the permutations that contain EAF in that order, I can argue, well, by symmetry, I'm going to have, if I put EA and F together, and I look at all of the other letters separately, I'm going to have 5 characters. So that's also 5 factorial. And then what do I have to subtract from that? So inclusion, exclusion is BGE union EAF equals the size of BGE plus the size of EAF minus BGE and EAF. So if I have to have both BGE and EAF, I get, what do I have? This is one character, this is the other, and I'm left with D, I think. All right, so then all of the permutations where this is together and this is together, I have 3 items, it's 3 factorial. So I'm going to subtract 3 factorial. Okay, so 7 factorial minus 5 factorial plus 5 factorial minus 3 factorial. Let's see if we got that right. But I'm going to go to Wolfram alpha. Wolfram alpha. So 7 factorial minus 5 factorial plus 5 factorial minus 3 is 4806. Right, so that's what we wanted to prove. Okay, good. Questions on that? Yeah. Yeah, the slides or this? Oh yeah. Did I write it wrong? Maybe it's yeah. That's, yeah, you're right, but it's still 3. Yeah, excellent. Yeah. No, very good. So that's true. If I have BGE and EAF, I have to write them like this. And then what did I miss? C, right. All right, perfect. Okay, yes. So I got lucky there. I did it wrong, but I got the right answer. But yeah, excellent. Good. Other questions? Okay. So yeah, we'll stop there for today. Yeah, what is today? I guess I'll see you guys next week. All right.